In our last lecture, we looked at rate laws. And rate laws expressed rate as a function of concentration. What we're wanting to do now is we're going to use those rate laws to develop a relationship between time and concentration. And this relationship between time and concentration is going to be different depending on the order of the reactant. So, without further ado, let's look at the relationship between time and the concentration of a reactant for a first-order reaction. I should also note that I'm going to be trying to pick up some time here and make up for some of the slowness of my other lectures here. So I'm going to be going very, very fast and doing a very practical approach to this lecture as opposed to a theoretical one. All right, first of all, review rate laws, the relationship between rate and concentration. What we're going to be dealing with now is our integrated rate laws, which expresses the relationship between concentration and time. And an integrated rate law is exactly what it sounds like. In an integrated rate law, you arrive at it through integration. All right, let's take a look at a first-order reaction. A first-order reaction would have the changing the concentration of A divided by the changing concentration of time is equal to a constant times the concentration of A. Remember how on one of our previous examples we replaced those triangles, those Greek letters deltas, with D's. D's and deltas are the same thing. If you've had math class, though, you know that D is the product of differentiation. One other thing, all of our reactions are expressed in terms of reactants, and reactants always decrease. So our rate is really a negative there. It's really the opposite of a positive rate. So with that in mind, we can do a little bit of rearranging algebraically, and we can say get our A terms over on the same side. Then all we need to do is now integrate this equation that we just rearranged. On this side, we rearrange it from an initial concentration to a concentration at a time t. And our time, we integrate, and I dropped a d over here, didn't I? dt. And over here, for our time, we want to go from time of 0 to a time t. When we do that, we discover we get a negative. The integration of an a to the negative 1 power would be natural log of a. So we've got the natural log of a sub t minus the natural log of a sub 0 equals, and the dt integrates to just t. So we've got k times t over on that side. Distribute that negative sign in. T. A little bit more algebra here. Multiply through by a negative 1. And that gives you a t minus natural log a sub 0 equals negative kt, or natural log of a T equals negative KT plus the natural log of A sub 0. In other words, the change in concentration over time for a first order reaction is shown there. If you can't read my chicken scratch or didn't follow that, don't worry. Remember, algebra isn't a prereq for this course. It's just something you take if you're really serious about being a scientist, and I know all of you are, so you'll be signing up for your algebra classes, your calculus classes shortly. But at any rate, you don't need to know calculus. I was just showing that for those of you who have had it. What you guys need to remember is this. The relationship between concentration and time for a first order reaction is the natural log of the concentration is equal to the opposite of the rate constant times time plus the natural log of your initial concentration. If we blow up this equation here, the equation we just derived on the other page, you can see how this fits that y equals mxb format that we love so much, where y would be the natural log of t, your slope would be the opposite of the rate constant, time would be your x, and your intercept would be the natural log of your initial concentration. In addition to memorizing this formula, there's another form of this equation that would be really helpful if you knew. We can also write this equation by subtracting the natural log of the initial concentration from both sides, like that. I would write that down in your notes. There are going to be some homework problems that we'll look at here in a second, and that you'll have to do in mastering. That will be really impossible for you to do without knowing that formula. Why don't you write down X files? Write down X files. X-F-I-L-E-S. Write down X files. Attempt to strengthen the relationship between what we do in the classroom and what we do in lab. You need to understand how the integrated rate law here corresponds to a graph. If you look at this, a graph of your first order rate law would be linear when we graph the natural log of A as a function of time. Not only that, but look at your slope. The opposite of your rate constant is your slope. The rate constant is always positive, by the way, so that means our slope is negative. So a plot of the natural log of A versus time should look like that. This makes sense. After all, A is a reactant, and as a reaction progresses, the amount of reactant decreases because it's being consumed. So, on an exam, if you were asked what graph would represent a first-order equation, you would look for one that would have a natural log of A versus time, and one that had a slope going down. If they asked you for the rate constant and they gave you a graph, what would you do? You'd calculate the slope, because the slope is the opposite of the rate constant. When you plot a first-order equation, a simple plot of reaction concentration versus time, you get a downward curve. By the way, those of you who allowed me for lab, we're actually going to do this in lab. We're going to measure the change of concentration of a reactant versus time, and you're going to test it by plotting various graphs to see if it's first order, second order, or zero order. Okay, this is more of what I already said, so we're just going to move on here. Again, this is just an example of how if I gave you a graph of the natural log of a substance versus time, and you can see it's a first order equation. How can you tell it's a first order equation? Because it's linear. And because it's linear, we know that the slope is going to equal the opposite of k. So I can solve for k by calculating the slope of this line here. So to simplify our process here, I'm just going to choose 2 points at random. I'm going to choose those 2 points to determine my slope. So I've got a negative 4.423 minus a negative 4.255 divided by 300 minus 200. That gives me a negative 4.423 minus a negative 4.255. That gives me a negative 0.168 divided by 100. And that gives me, why am I even looking for my calculator? That gives me 1.68 times 10 to the negative third inverse seconds for my K value. So you can take a graph and you can use it to solve for the rate constant for a reaction. Continuing our warp speed journey, let's take a look at some problems that we're going to have to solve using our integrated rate law for a first order reaction. The great thing about the integrated rate laws is they're plug and chug. The decomposition of hydrogen peroxide in a dilute solution of sodium hydroxide is described by the equation as shown. The reaction is first order in hydrogen peroxide. The rate constant is shown, and the initial concentration is shown. What is the concentration of hydrogen peroxide after 4 hours? First thing I like to do when I'm working these rate laws is I like to identify and label. First, I realize I'm working with a first order reaction because it tells me. That means that my rate law that I'm going to be using is that. Then as I read the problem, they tell me that the rate constant is 1.8. So I know that that is 1.8 times 10 to the negative fifth inverse seconds. Then they tell me my initial concentration is 3.0. And they want to know the concentration after 4 hours. So they tell me that my time is 4 hours. Now, right away, there's a danger, Will Robinson, danger situation occurring here. Because they gave me a rate constant in inverse seconds, and they gave me a time in hours. So I'm going to have to convert hours to seconds, but that's not a big deal. 4 hours, 1 hour is 3,600 seconds. So that means my time is actually 4 times 3.600, 4 times 3,600 equals 1.44 times 10 to the fourth seconds. So now I just have a straightforward plug and chug situation here, where I have the natural log of AT, of A at time t, is equal to a negative 1.8 times 10 to the negative fifth inverse seconds times 1.44 times 10 to the fourth seconds plus the natural log of 0.30 molar. So I grab my calculator, and that gives me a negative 2.5, whoops, 9. Oh, well, you know, heck what? Just a second, I'm going to write that even better. A negative 0.259 plus, and then the natural log of 0.3. So natural log 0.3, a negative 1.20, negative 1.463 equals the natural log of a sub t. Now I'm wanting a sub t, and a sub t is inside my natural log. So how am I getting rid of that natural log? I'm raising both sides to the e. If you're using the calculator I recommend, what you can do is if you hit second natural log key, that will give you your e to the x function. So second e to the x, second answer, and that gives me a concentration of 0.2, and let's see, only the decimal points are significant when we undo that, so 0.23 should be the answer to the correct sig figs. Your book plays fast and loose, and I think they actually go 0.231 if you look there. But that's your concentration at time t. All right, so that's the answer to A. Let's try B here. B says, how long will it take for the hydrogen peroxide concentration to drop to 0.2 molar? So this time, they've given me A sub t, and they're wanting me to solve for a time. So I've got my natural log of A sub t equals the opposite of kt plus the natural log of A sub 0. So I have the natural log of 0.12 molar equals a negative 1.8 times 10 to the negative fifth inverse seconds times t plus the natural log of my initial concentration, 0.30 molar. Alright, so now we entered the plug and chug phase. Natural log 0.12, negative 2.12. Oh, by the way, now is the perfect time for you to write down Battlestar Galactica. Write down Battlestar Galactica, Battlestar Galactica. Woo. Battlestar Galactica. Natural log of 0.3 is a negative 1.20. Alright, we're going to simplify by adding that 0.1 to both sides of our equation. So we have a negative 2.12 plus 1.204 equals a negative 1.8 times 10 to the negative fifth inverse seconds. And that's a 5 there. Wow, it's really hard to do curves with this thing. And that crosses out that, and that gives us 2.12. That gives us 0.916 equals a negative 1.8 times 10 to the negative fifth seconds inverse times t. Divide both sides, 1.8 times 10 to the negative fifth inverse seconds. Oops, I forgot my negative sign over there. Dividing both sides by a negative 1.8 times 10 to the negative fifth inverse seconds. And that gives me, that's going to go to 1. And that's going to give me t equals that gives me 5.1 times 10 to the fourth seconds. Ta-da! Chemistry is easy, life is hard. Let's keep moving and look at another example here. All right, let's look at C. C asks, how long will it take for 90% of the hydrogen peroxide to decompose? For the purposes of this example, let's pretend that they didn't give you this piece of information. Now let's try solving it without using that piece of information. They want to know how long it'll take for 90% of the hydrogen peroxide to decompose. So, what is the relationship, therefore, between A, the concentration at times T, and the concentration initially? What's that relationship? They said that 90% will decompose. If 90% of the hydrogen peroxide is decomposing, remember, A sub T is the amount left. So if 90% is decomposed, 10% is left. So that means that our concentration at times T is going to be 10% of A sub 0, or we could think of it as 0.1 times our initial concentration. If we know that relationship, we can work this problem because of the wonderful nature of the first order integrated rate law. We know that there are two forms of the integrated rate law. Remember I told you there was one that would prove useful to you in your future endeavors? By subtracting the slope, the natural log of A sub 0, from both sides, you can rearrange that first order rate equation to be the first order integrated rate law to this format. This format frees you from knowing the initial concentration, as long as you know the relationship between the initial concentration and the existing amount. For example, in this problem, we know, because we just talked about it, that A sub T is equal to 0.10 A sub 0. So if I come over here and say 0.10 A sub 0 is my concentration at time T, and my initial concentration is A sub 0, then I have a problem I can solve. Why? Because any number divided by itself is 1. So the problem suddenly becomes one of ridiculous simplicity, because I now have the natural log of 0.10 equals the negative kt, and they gave us the k in the problem. So now it's plug and chug city. natural log 0.1 is negative 2.30 equals negative 1.8 times 10 to the negative fifth second inverse times t. That equals, now we divide both sides by the rate constant, negative 1.8 times 10 to the negative fifth inverse seconds, negative 1.8 times 10 to the negative fifth inverse seconds. That goes to 1, and that gives me a t equal to 1.8 second e negative 5. 1.3 times 10 to the fifth seconds. Ta-da! Chemistry is easy, life is hard. What can I say? Why don't you write down Farscape? Everybody on that TV show had it hard. Write down Farscape. F-A-R-S-C-A-P-E. Farscape. All right, let's define a new term, one that's going to be with you quite a bit, and that's half-life. One way of quantifying or expressing to other people the rate of a chemical reaction is to talk about its half-life. Half-life is the time required for the reactant concentration to drop to 1/2 of its initial value. This is a unit of speed, so to speak, particularly favored when it comes to radioactivity or nuclear reactions. But it means the exact same thing, that basically how long does it take for half of your initial amount to disappear? For a first order reaction, only, the half-life is a constant. The half-life is constant, and the half-life of a reaction is always equal to 0.693 divided by the rate constant. And if you think about it, the proof of it's really simple. Here's our integrated first-order rate law. At the half-life, by definition, the concentration at A sub t is 1/2 A sub 0. So you have the natural log of 1/2 of A sub 0 divided by A sub 0 equals the natural log of 1/2, because our A sub 0s have gone to 1, and the natural log of 1/2 is a negative 0.693, so you divide both sides by a negative k, which makes it positive, and you get 0.693 divided by k. So the half-life for any first-order reaction is going to be 0.693 divided by its rate constant. First-order reactions are the only reactions where consecutive half-lives are the same. What do I mean when I say that for a first-order reaction, consecutive half-lives are the same duration? Well, you can have more than one half-life, right? If you start off with 100%, the time it takes for your concentration to fall to 50% is one half-life. The time it takes for that 50% to fall to 25% is also a half-life. So that would be your second half-life. The time it takes for that 25% to fall to 12.5 percent of your initial amount would be your third half-life. For a first-order reaction only, your first half-life is going to equal your second half-life is going to equal your third half-life is going to equal your fourth half-life. For a first-order reaction, the length of the half-life doesn't change. This leads to some really fun things you can do in terms of the math and half-lives and first-order equations. This graph illustrates what we were talking about. Notice that your time interval here between your first half-life and your second half-life is the exact same as it is for your third half-life. For a first-order reaction, the half-life is independent of the initial concentration. Each successive half-life is of equal period of time. You can do this neat equation for a first-order reaction, or for any for a first-order reaction. For a first-order reaction, your concentration at time t is equal to your initial concentration times 1/2 to the n power, where n is the number of half-lives. How would this formula come in handy? It would come in it would become very useful in solving things like this. Example magically appearing on your screen. The half-life for the decomposition of compound X is 42.2 seconds. How long will it take for 66.6% of X to decompose? Remember, always read these examples carefully. Always read whether they want you to have 66.6% of X left, or whether they want 60.6% to be consumed. In this example, they're talking about how long will it take for 66.6% of X to decompose. That means that we're going to have 33.4% left. So that means that my concentration at time t is going to be 33.4% of my concentration of A sub 0. Or, if I assume that I started with 100 moles of A sub 0, then, or rather, if I let A sub 0 equal 100, then my A sub t would be 33.4. You following where I'm going with this? So now I can plug into this equation. Why do I have to go to that equation? Because they gave me a half-life. They didn't give me a value of K, so I can't use my other equation. If I wanted to, I could solve for my value of K since I know my half-life, but I'd much rather do it this way. So I have 1/2 times n times 100 equals 33.4. Divide both sides by 100, so I have 1/2 to the n power, now equal to 0.334. And you're saying, I don't know how to get that answer for n there. Not a problem. It's really quite easy. When you can't get a log, what do? You raise. What do you do when you can't get a power? You take the log of both sides. And when you take the log of both sides, that allows you to pull the n out. So now you have n times the log of 1/2 equals the log of 0.334, which means n equals the log of 0.334 divided by the log of 0.5. That gives you n being equal to no, I punched in my calculator wrong. Log 0.334 divided by the log of 0.5. There we go. That gives you 1.582. And what's n? N is number of half-lives. So I have 1.58 half-lives. And according to my problem, each half-life is 42.2 seconds. So 42.2 seconds times my half-lives gives me 66.7 seconds. Ooh, that's weird how it worked out. Gives me 66.7 seconds is how long it would take for 60.66% of my initial amount to disappear for the decomposition of X. And that's a very useful formula to have. That's just a good tool to have in your arsenal. All right, let's take a look at some of these examples here. I don't want to do all of them. For example, I'm going to skip this one here in the interest of time. Let's skip straight to B here. Calculate the half-life from the rate constant. We know that the half-life equals 0.693 divided by K for a first-order reaction. So 0.693 divided by the rate constant they gave us. Plug it into your calculator, and it has 2 sig figs here, so it should really be 410 seconds. I believe your book and your calculator will show you 408. So that's easy. Plug and chug. We love plug and chug. It's practically like a Christmas present on the test. What we want now is we want C. Let's take a look at C. The initial concentration of dinitrogen pentoxide is 0.02 molar. What is the concentration of dinitrogen pentoxide after 5 half-lives? Okay. A couple ways we can do this, the easiest of which is to use that formula I just gave you. A sub t equals 1/2 to the n power times A sub 0. So I want the concentration of A sub t after 5 half-lives if my initial concentration is 0.020 molar. So that's a matter of plug and chug. So I go 1/2 hat to the 5th times 0.02 equals 6.25 times 10 to the negative fourth. Alrighty then. Let's take a look at D. How long will it take for the dinitrogen pentoxide concentration to fall to 12.5% of its initial value? So from the way they have it phrased there, they want your A sub T to be 12.5% of A sub 0. So that's going to be a straightforward plug and chug here, where we plug in 12.5% is the same thing as right, that would give us 12% of our initial amount. So A sub T is that, 0.125 A sub 0 divided by A sub 0 equals a negative KT. They gave us K there in the problem, so we'd plug it in there. A sub 0 divided by A sub 0 equals 1. So now it's simple plug and chug, and we've worked it before, and let's keep moving. Real quickly, we want to look at first order reactions in the context of radioactive decay. Really, there's nothing new here except for some terminology. First, they like to use the term decay rate when they're talking about radioactive decay. And that radioactive decay rate is equal to the change in the number of radioactive nuclei divided by the change in time. And that's going to be equal to, because it's a first order reaction, the rate constant times the number of radioactive nuclei. Really, if you think about it, all they've done is rewritten this as a all they've really done is rewritten our first order rate law here. They've just said rate is equal the opposite of the change in the concentration of A divided by the change in time equals K times the concentration of A. Therefore, radioactive decay is really just a first order reaction, and we can feel free to use any of our first order formulas, substituting the number of nuclei for molarity. The decay constant for sodium-24 is 4.63 times 10 to the second inverse hours. What is the half-life of sodium-24? Again, this example is really just to adjust you to the terminology. This decay constant is what they call the rate constant. So this is really your value of K, right? Decay constant is a synonym for rate constant. Your decays are nearly always first order. If they don't say otherwise, assume decays are first order. They want to know the half-life. Remember, half-life is 0.693 divided by K. So 0.693 divided by 4.63 times 10 to the negative second inverse hours equals 0.693 divided by 4.63 second EE negative 2, and they've given us 3 sig figs. 3 sig figs would actually wind up being 15.0 hours. Chemistry's easy, life is hard. This is nothing new. It's just applying new terminology to our integrated rate laws that we've already met. This is fun just for the algebra. The half-life of radon is 382 days. What is the decay constant? So once again, we're using the same formula we did last time. This time, however, they've given us the half-life. And they're wanting us to solve for the decay constant, or the rate constant. Be careful. Your variable's on the bottom here, right? So the first thing you have to do is bring it to the top. So you're going to multiply both sides by k. Otherwise, you wind up solving for the inverse of k. So the first thing I'm doing is I'm multiplying both sides by k. So that gives me 3.82 days times k equals 0.693. So k equals 0.693 divided by 3.82 days. That gives me 0.693 divided by 3.82. It gives me a rate constant of 0.181 inverse days. Chemistry is easy, life is hard. I like this problem. Let's take a look. Phosphorus 32 has a half-life of 14.26 days. What percentage of a sample remains after 35 days? Well, what we're going to do is we're going to assume an initial amount of 100, and we're going to want to solve for a sub t. They've only given us half-lives. So I want to use my formula where a sub t equals 1/2 to the n, to the number of half-lives, times a sub 0. If you look at what they've given us, they're wanting us to solve for a sub t. They've told us that we have 100 of our initial amount, and then we need a number of half-lives. We have to get one of these two variables. They've given us the number of half-lives indirectly. They've told us the length of a half-life, and they've told us the days. So our number of half-lives would be our number of days divided by the number of days per a half-life. So my number of half-lives is going to be 2.45 lives. So now I can plug and chug. And I'm putting that in my calculator, by the way, by going 100 times, and then I'm opening parentheses, 1 divided by 2, close parentheses, and then I'm using my arrow key to punch in up arrow 2.45. And when I do that, I get 18.3% left. chemistry's easy, life is hard. Why don't you write down G-force? G-force. G-F-O-R-S-E. Here's one of the more interesting examples I've ever seen in a textbook, and that's why I've really decided to work it. It really requires you to understand what they're talking about here. A sample of argon-41 decays at an initial rate of 34,500 disintegrations per minute, but the decay rate falls to 21,500 disintegrations per minute after 75 minutes. What is the half-life of argon-41? None of the equations that we've really learned up until this point can help you solve this, because all they've given you is two rates in a random time. This really has to do with the method of initial rates. We have a decay process here, so if we assume that it's first order, then our initial rate is equal to K times the concentration of argon that we had initially. They've told us that that initial rate is 34,500 disintegrations per minute. They've also told us the rate after 75 minutes. And they told us that rate after 75 minutes is 21,500 disintegrations per minute. And they want to know the half-life for this reaction. All right, so let's take a look at what we've got. We know, looking at this method of initial rate setup that we have, that anything divided by itself is equal to 1. So we can actually cancel out our values of K. So I now know that the ratio of my initial amount of argon divided by my amount of argon after 75 minutes is equal to 34,500 divided by 21,500. So I'm going to put that into my calculator. 34,500 divided by 21,500. And that gives me 1.60465. So I have the ratio of argon 75 after 75 minutes to argon that we had initially. What we'd really like, however, would be the inverse of that ratio. What am I talking about? Bear with me here for a second. I think it's easier once I've done it than to try to explain what I'm doing. Let's take the multiplicative inverse of both sides of that equation there. When I do that, it gives me the fraction of argon remaining, right? So I'm going over to my calculator, I'm hitting my x to the negative 1 button, or I'm taking 1 divided by 1.6046. And when I do that, that gives me 0.623 is the fraction of 75 remaining. In other words, if I was to put this in percentage terms, just so that you can see where I'm going with this, I've got my amount of argon after 75 minutes here divided by my initial amounts of argons. If I multiplied that by 100 on both sides, that would give me a percentage. In other words, (62.3% of my initial amount of argon, I'm bringing my bottom up over here in addition to multiplying by 100, is how much argon I have left after 75 minutes. How does that do me any good whatsoever? Here's how it does me some good. My end goal here is to get the length of a half-life. I now know what percentage of my initial amount remains after 75 minutes. I can then take this relationship and go to that half-life formula that we've used time and time again, where we say so for this scenario, we're going to say by substitution, 0.623 a sub 0 equals 1/2 to the n a sub 0, and I keep saying a because we're using argon, same thing there. So that means that we can cross out that a sub 0, and we're now at 0.623 equals 1/2 to the n power. So I can solve for my value for n by taking the log of both sides. So I've got the log of 0.623 divided by the log of 1/2 equals n, and that gives me .683 half-lives. So that's my number of half-lives. Alright, that's great, but I still don't have a length for my half-lives. Or do I? Remember, what was our initial premise way back at the beginning? We were relating the concentration after 75 minutes. So that means that 0.683 half-lives equals 75 minutes. So how much would one half-life be? If 75 minutes equals 0.683 half-lives, then one half-life equals X minutes. So one half-life is equal to 110 minutes. My calculator, in case you're curious, actually reads 109.86 minutes. But we've got two sig figs with our 75 minutes. So the half-life would be 110 minutes. And this is what I would consider an extreme problem. But it's doable. It's extreme. It's towards the upper level of the difficulty I would expect for this class, but I do think you're capable of doing it. And you may encounter it again in the homework.